Okay, now if we have conduction through a cylindrical surface, no, it is actually different. No, the formula is different for conduction, and let me explain why. No, so remember the Fourier's law, which is this one, the Fourier's law. No, so the Fourier's law states that this is true, no, but instead of x, we have the radius, no. So the radius varies as heat transfer from the inside to the outside of the cylindrical wall. So what can we do here to find the actual uh, derivation? Conduction cylinder, which is negative Ka dt over dr, is we can still do the same treatment, no, basically. So we can do this as variable separable. So you have q on sil, no? But we have to take note that the area here, what is the area here? What is the area of the cylinder? So the area of the cylinder is, so the heat is transferring from this to this, no? So the area parallel, or sorry, perpendicular to this, as we discussed before, is actually the lateral surface area of a cylinder. So the area of the cylinder is actually 2 pi L, 2 pi RL, or pi DL. So this is three dimensions, right? You have this three dimension, this is your, this is, let's say this is three dimensions, so we have the length here. Okay, so we have to write this first, no? So negative k and then 2 pi or L, no? And then dt over dr, no? So doing the variable separable, no? You have q cont sil, or just write q, and then you have dr, okay, and then you have r. So variable separable, right? So your r here is cross multiplied, and then you have negative 2 pi k L and then dt. Is that okay? So the variables are separated here now. You can just integrate this again. Okay. So we are assuming that Q is constant. We're assuming that P is constant. The length is also constant. No, it is not changing. But the R is actually varying now, as you can see. Why is it varying? Because initially, no, if you can imagine the transfer, no. So this is the first R. For example, this is the first R. But as it goes through the wall of the cylinder, the R changes, no? It is changing over time, right? So we have to consider this as well, yung R now. So if we change this, sorry, if we solve for this, the integral of this, and also including the limits. So the limits here is you started with R1, right? So R1, and then you ended with R2. In temperature, you started with the hot, no? T1 here below. And then you have T2 outside. So solving for this, we have Q, and then you have the integral of dr over R is actually ln R, absolute value of R. Okay? And then this should be evaluated from R1 to R2. And then negative 2 pi KL. And then you have T, no? Evaluated from T1 to T2. So if you solve for this or simplify this definite integral, you have Q ln R2, no? Minus ln. So we are assuming that R is positive anyway. So I'll just remove the absolute value. And then ln R1. So you have 2 pi, negative 2 pi KL, and then you have T2 minus T1. So we can transpose this negative sign here, and then you actually get to combine here this, no? So you can represent this as ln R2 over R1, no? That makes sense. No? And then you have negative positive 2 pi KL, you have T1 minus T2. Okay, so if you simplify this, the heat transfer rate will become 2 pi KL T1 minus T2, and then all over ln R1 or R2 over R1. Okay, so as you can see, this is also area. So you can also write this down as area Actually K, only this part, no, sorry, with this part. So you have area, and then you have K, and then you have T1 minus T, and over ln R2 minus R1, R2 over R1. Okay, so this is 4 cylinders. Okay, now what can happen is that you have different layers as well of materials of your cylinder, no? So for example, if you have a pipe, you have an insulation of a pipe. Okay, so it has another layer. So the same thing goes with cylinders. You can just add the effective resistances, no, of your cylinders, and then you're good to go. If you find the total resistance, you can find the heat transfer rate. No? So if in that case, as you can imagine, no, if this is the scenario, then if we have here, you have this the convection layer, and then you have a conduction layer here. You have another conduction layer, another conduction layer, and then another convection layer. So adding these thermal resistances, you will have the effective resistance. You can solve for the heat flow rate. No, so that's like basically it. No, it is the same with what we've done so far in the plane surface or plane wall surface, but we just have another formula to understand. No? So take note of this. Take note of this as well. No? These are different ratios. This is usually the outside, inside, outside, inside. No, just take note of that. So there is a phenomenon on insulation, or when you have multiple layers of, or if you have a layer of insulation of cylinder, wherein if you vary the radius or the thickness of the insulation, the heat transfer rate will increase, starting from a very, very thin layer of insulation here. If let's say you have a thin layer of insulation here, as you increase the layer of insulation or the thickness of the insulation, your heat transfer will actually increase, right? If you can imagine, because you are increasing the what? No, you're increasing the actually the area, no. So the area here, no, if you can imagine. So this is a three-dimensional cylinder. So if you increase the R, no, right? Increase the R, you will get an increased surface area. So you will increase the surface area, therefore, your convection, no, will have a lead through your will be dominating the heat transfer. No? But as we increase the radius or the thickness of the insulation, if we steadily increase the thickness of the insulation, there will come a point where increasing the insulation will actually decrease the heat transfer rate. No? So it will increase and then it will decrease. So at this portion, this is convection dominated, no? Convection dominated heat transfer, dominated by convection, but in here it is dominated by conduction, no? Dominated. Okay. So at this point is where the convection and the conduction are balanced, you know, in between it and with and this radius here, right here, which is somewhere in the middle here, is your radius or the critical radius of insulation, which can be found actually if you find the derivative, no, of your Q. Find the derivative of this. Sorry. If you find the first derivative of this and then equate this to 0, no, with respect to R2. No? But anyways, there's a shortcut method, no? The radius of the critical radius of the insulation is just K over H. So K is the thermal conductivity of the insulation material, and H is the convective heat transfer of the outside wall. No? So that's it. No? We have another term, only the critical radius of insulation. Now, same goes for spheres. No, we've discussed the cylinder. We also want to discuss the sphere. generally we have the same treatment. No, we can represent the resistance, no, with spheres. And if you derive actually, you can solve for this. The derivation of this, I think you can do this on your own, as an assignment, no, to solve for this. And then the critical radius is also 2k over h. Oh, sorry, it is multiplied by 2 compared to the cylinder. Okay, so that's it.